Okay, everyone, it's time to get started. So, as you can see from the front screen, today is volcanoes, but associated with the core volcanoes is igneous rocks. So we also need to understand the rocks in order to understand why we have such different volcanic activity around the country. I'm really sorry about the microphone cutting in and out. There's nothing I can find that's wrong with it, but if it keeps doing it, we'll see if we can get it fixed. So, lecture 8, we're 8 in now, and I wanted to show you this really beautiful picture to show you that we don't need Hollywood to make the world more exciting than it already is. This is the eruption from the volcano name that I can't say because I'm not Icelandic, which is yt5s, something like that. And you can see in the base here, that's the glacier. That's the ice cap that it erupted through, and it produced this amazing ash plume, and associated with ash plumes you get all of these lightning strikes. And there was actually webcams watching this, so I spent a lot of my afternoons watching this ash plume, watching the volcanic activity. Not a productive week for me, but it was still really fun. Okay, so, what's wrong with this? Oh. That would help. I need to actually start the software for it to work. Okay, give me 1 second. So we were going to review quiz 2 right now, but unfortunately Triple E was down for quite a lot of hours yesterday, and so I extended the deadline for quiz 2 until 6 p.m. And hopefully that will give everyone a chance to complete it. Okay, so no quiz 2 review, but I will review it on Wednesday because I know that quite a lot of people found this tricky. And it's meant to be somewhat tricky. If you get 20 out of 20 the first time round, then I'm really not doing my job properly. Because you have to think of me like a personal trainer for your brain. If you go to the gym and you pay for a personal trainer and you do 2 sit-ups and you go, I'm done, then they're going to yell at you. It's their job to yell at you and get you to do more. Well, that's the equivalent of what I'm trying to do. I'm trying to challenge you to get you starting to think like scientists and apply the information. And that's always going to be more difficult than simply recalling things. So don't stress out if you don't get 20 out of 20 every time on your first try. As long as you're learning, as long as you can see where you went wrong and put things together. Okay? And a reminder, I'm in a meeting from 9 till 4 today, and I've escaped to talk to you, but then I have to go back. So no office hours today. Midterm. Everyone's so excited. Midterm 1 is a week today. Okay? It's come up quickly. It's going to be in this room from 1 till 1:50, so normal class time. It's going to be about half multiple choice on a Scantron and half short answer questions, things like drawing out a feedback loop or doing a little calculation or labeling something on a map, things like that. It will cover lectures 1 to 9, so it won't cover Friday's lecture. So Friday we're going to talk about the atmosphere for the first time. That won't be in the final, the midterm on Monday. There will be assigned seating. If you are a left-handed student, the right-handed people among us would be extremely happy if you could let me know, because we have a full classroom. And so unfortunately, we never have enough left-handed people for the left-handed seats. So some of you right-handed people might end up in the left-handed seats, and I'm sorry about that, but there's really nothing I can do about it, apart from promise you it won't happen again for the next time round. Okay? So please do let me know if you are left-handed. Things you will need: a pen and pencil, Scantron form, the 288, it's F288, it's a red one. Your student photo ID, so we know that you are who you say you are. And for the first time, this is new for students that have had me in the past, you can bring a little note card of notes. Okay, because there are a lot of new words, a lot of new terms in this class, and I'm not interested in testing your memory. I'm sure you all have good memories, you're here. What I'm interested in seeing is whether you can use information and apply it. So you can bring a note card, double-sided, of notes with you to the exam, which you will hand in at the end. Okay? A study guide will be available on the website as soon as I can upload it. I tried last night, but it wasn't working, so I will do that. I'll also probably upload some practice questions. And then lastly, I'll be in my office from 9:30 to 11:30 on Monday for last-minute questions, if you have any. Does anyone have questions about this? Yes?
You give a calculation question, will you give the formula?
I will give you the formula, absolutely. I'm not interested in you memorizing formulae either. Okay? Any other questions? Yes?
How do we let you know we're left-handed?
Send me an email, please, and then I will put you in a left-handed seat. Great. Okay. Nothing else? Okay. And then lastly, the TAs will be holding a midterm review session. It's going to be on Thursday, not in this room. It's going to be in HIB 100, which is just the other side of the Student Centre. So look at your notes, bring your questions for the TAs, and it will be at 6:30 on Thursday evening. Okay? Right, so what are we going to do today? We're going to think about, it's a solid. It's naturally occurring. So it ticks all of our boxes, okay? So ice, in this definition, is a mineral, yes?
I thought we were talking about room temperature.
Ice, well, you can have ice existing briefly at room temperature, but yes. Okay, so not only is our crystals very important, but obviously they can be very beautiful as well. So this is not photoshopped. This is a real photo taken in a cave down from Mexico. And they were digging a really deep mine, and they broke into this chamber with these amazing crystals that have had just the right conditions to grow for a very, very long time, and they are just spectacular. It really looks like something out of Superman or a movie in some way. So these things can get big. Okay, so let's think about our common minerals, because minerals are really what make up rocks and what make up the earth. And so we have a lot of what we call silicates. If you look at the amount of silicon and oxygen in the crust, then they make up the bulk of the crust. And so silicates, which are that Si4 little group, are what make up a lot of the Earth's crust, and what we're going to talk about today when we talk about volcanoes. So things that you might have heard of that are silicates are feldspar, quartz, clays, micas, things like that. Then we have oxides. Those are really helpful for finding minerals with metals in them, so things like iron oxides, aluminium oxides. We have carbonates. We have our limestones, things like calcium carbonate. We have sulfates, gypsum, and then we have sulfides, things like pyrite, which is that fool's gold, if you've ever seen fool's gold. So we have a whole bunch of different minerals. Don't worry too much about them, but they exist, okay? So what is a rock? We've talked about what a mineral is. What's the difference between a mineral and a rock? Well, a rock is naturally formed again, just like our minerals. It's non-living, so non-organic. It's solid, so we're still the same as our mineral right now. But the difference is that a rock is made up of a lot of different minerals. So it doesn't necessarily have one specific crystalline structure. It doesn't necessarily have one particular chemical formula that defines it. It's a mixture of lots of different minerals all lumped together. Okay? So, is concrete rock? So see if you can follow the definition again. Is all the concrete we see around here, is that rock? Couple more seconds. Okay. Oh, we've got a majority this time, and the majority would be right. Which criteria does it not meet from my definition? It's not naturally formed. We've made it. It is a collection of other minerals and stuff, but it's not naturally formed. We created it. Okay. So we have 3 different types of rock. And this is probably starting to sound familiar. We have igneous rocks. And igneous rocks are what we're going to talk about today. And they're formed by cooling and consolidation or crystallization of magma. And magma is sort of molten rock. We have sedimentary rock, and sedimentary rocks can be formed in quite a variety of ways, but fundamentally they either form by chemical precipitation of dissolved material, so things like calcium carbonate can precipitate out of solution, halite, gypsum, things that precipitate out of seawater, or they can form by the deposition of mineral particles transported by water, wind, and ice. So if you go to the beach, you can see lots of sand that has been transported by water, and dunes are transported by wind, and ice travels and carries sort of particles along with it. So these are our sedimentary rocks. So once these things get sort of deposited by wind, water, and ice, or by chemical precipitation, they can form rocks. And then lastly, we have metamorphic rock. And metamorphic rock is what happens, well, it's what you get if you take an igneous rock or a sedimentary rock and you heat it up, or you put enormous amounts of pressure on it, and that's what you end up with. Okay? So what do you think? Which of those three do you think is the most important for the crust? What do you think it might be? I heard an igneous over here, and you would be right. Igneous rocks make up 95% of the Earth's crust. So igneous rocks make up 95% of the Earth's crust. We don't necessarily see all of that because a lot of those igneous rocks are actually much deeper down. What we tend to see at the surface is the effect of our wind, of our ice, of our water. It's the sediment and the sedimentary rocks. That doesn't mean that deep down we don't have enormous amounts of igneous rock. So let's talk about it some more. And first of all, we need to talk about magma. So magma is this sort of definition, a mixture of molten rock, suspended mineral grains, so it can have bits of solid in there as well, and dissolved gases that forms in the crust or the mantle. And we're going to look at the different environments that magma can form in today. Guys at the back, do you want to be quiet, please? Oi, you three. Shush. Okay. So lava, what we think of as lava, is basically just magma that reaches the surface. So it's magma when it's within the crust or the mantle. Anything that makes it out to the surface is called lava. And we characterize magma based on its composition, based on its viscosity, which is the ability to flow, and the temperature. So we're going to look at three different types of magma. We're going to simplify it a little bit. We're going to look at basaltic magma, andesitic magma, and rhyolitic magma. So these are the more complicated words that your note card is for the exam. So the main fundamental difference between each of these is that as you go from basaltic magma, that has a composition that's 50% silica. So that combination of silicon and oxygen is a silica, and basaltic magma is 50% that. If we go to andesitic magma, it's 60%. If we go to rhyolitic, it's 70%. And that actually has a very important control on things like viscosity. So who's been to Hawaii and seen the lava flows? Yeah? How did they flow? Did they like clump together, or did they go relatively smoothly and fast? Yeah? So if you see when they're sort of first coming out, they flow pretty nicely. They're slow, they're rock, it's molten rock, it's never going to flow like water, but it flows relatively smoothly, it flows relatively fast, and that's what we call sort of low viscosity. So when it flows, when it's sort of runny, that's low viscosity. The andesitic in the middle is medium, but then when we go to rhyolitic lavas don't flow. They're really blocky, and they're really sort of sticky, and so they just clump together at the top. And then eventually a whole bunch of them will sort of slide off the side. But it doesn't flow. It's just sort of clumps there in the middle. And the reason that we have different amounts of silica and so different viscosities is because we have a different amount of melted continental crust going into each of those three different magma types. So with basaltic magma, we really don't have any, or only a tiny bit of continental crust that's melting and forming this magma. In andesitic, we have a little bit, and then in rhyolitic magma, we have much more continental crust melting and forming the magma. And why does the amount of continental crust matter? Because remember, our continental crust is sort of lighter, it has more silica in it than our ocean crust, which is denser and easier to sink back down. So that's why continental crust is important. And so I want you to have that in your mind when we think about the different places where we have volcanoes and the processes that are happening at those boundaries and forming our magma. And then the last thing that changes with each of these magma types is the volatile content. And when I say volatiles, I mean gases. So things like carbon dioxide and water vapor, which are the main gases in our sort of magmas. And obviously you can imagine that if something is quite runny, how easy do you think it is going to be for gas to escape from that? Pretty easy. If it's really sticky and it won't flow, it's going to be much harder for those gas bubbles to escape out. Yeah? Maybe? Yeah. Good. Okay. So, thinking about this, if basaltic magmas are runny and they don't have much gas content, and we can compare that with the rhyolitic magmas that have high gas content, and they're really sticky and blocky, which do you think is likely to be more explosive? Rhyolitic. Because we're basically building up a pressure cooker, right? We have a lot more volatiles, we have a lot higher gas content there. We're not letting it escape, and so it can build up and can build up and build up and goes bang in a big way. Whereas Hawaii doesn't do that. Hawaii has more basaltic magma, and so gases can escape pretty easily, and it also just flows out pretty nicely. So there's no sort of pressure to build up and explode. So in terms of our eruption intensity, basaltic magmas don't really create much sort of danger to us. We can get out of the way pretty easily. Their eruption intensity is pretty low. Then we go into medium for andesitic. Andesitic's always the medium one, unfortunately. And then rhyolitic, we have big, big explosions. To be honest, andesitic explosions you don't want to be in the way of either. They go bang in a very big way too. Okay, so let's think about where igneous rocks are. So I've already said that at the surface we don't necessarily see them, but they actually make up 95% of the Earth's crust. And so where is that? It's all deep down. And so we have two different types of igneous sort of settings. We have intrusive igneous rocks and extrusive igneous rocks. And which of those two terms do you think, or can you read quickly enough? Which of those two terms do you think describes rock that escapes from the top? Extrusive, yes, okay. So extrusive rocks are rocks that spread out at the surface. They're erupted at the surface and they cool down at the surface. Intrusive rocks cool down inside the crust. So hopefully those are two easy ones to remember compared to the others today. I don't want you to panic and memorize all of these different terms like laccolith, pluton, batholith. Those aren't necessarily important. All I want you to realize is that the magma and the lava that escapes out of the top of your volcano is a tiny, tiny, tiny fraction of the molten magma that's actually down there, okay? So your little volcano that you're seeing is sort of dwarfed in size by the amount of magma that you can get down, so deep down, okay? So extrusive igneous rocks are what gets erupted at the surface. So things like lava flows, ash, what we call tephra, which are sort of bits of rock that you see exploded out of the top. And they cool down really quickly. So they have very, very small crystals. Did anyone have to grow crystals at school when you were little, like the copper sulfate crystals? Yeah. Did you wait for one day or did you wait for much longer? Come on, dredge your memory. How long did you want to wait if you wanted big crystals? A long time. They take time to form, okay? And so the rocks that get erupted at the surface have very, very tiny crystals. That means that the intrusive rocks, the ones that cool down inside, they cool down much more slowly because there's all of this rock around them insulating them. It keeps them warmer for longer, so they slow down much more, or they cool down much more slowly, and so they have time to form really nice, beautiful crystals. Okay? So that's what the diagram shows you here. So which of those 4 rocks is an extrusive rock? Couple more seconds. Okay, so let's see. Excellent. Okay, D. Why is D the extrusive rock? It's got the smallest crystal size. In fact, it's so small that you really can't hardly see separate crystals at all. Whereas these others, A, B, and C, have nice big crystals. You can see the distinct different minerals that make up that rock. So, what's C? Does anyone know the name of the rock that's C? Begins with G?
Granite.
Granite, absolutely. So, who has granite countertops in their kitchen? Yeah, quite a few people. Look properly at that. I can hear a lot of talking at the back there. Please, can you guys be quiet? So, when you look at your granite table, your countertops, that rock that you have as your nice countertops actually cooled down. It was a magma chamber. It's rock that cooled down really deep within the Earth's crust. And I think that's really cool. Think again about what you're looking at when you see that. It's an ancient part of a magma chamber that you can see. Okay. So, the other reason I want to talk about this is where is there large amounts of granite in California? The mountains. Yeah, the Sierra Nevada mountains. If you've ever been up there, they look like that. They're huge areas of granite. And you can see that, remember that batholith, which is basically just this sort of lower section of molten magma that doesn't reach the surface, that cools down in place in the crust. The whole Sierra Nevadas are basically one giant batholith, or a whole series of batholiths. So we're talking about huge, huge areas and huge volumes of igneous rock here. Okay? So lots of granite in California. You have to enjoy it. So, onto volcanoes. So volcanoes are any vent or opening from which lava, solid rock, debris, or gases are erupted. And usually it's a combination of all 3 of those things. And they are very beautiful, and they are very violent and terrifying at the same time if you ever get close to one. And they're really important for Earth system science because, first of all, they erupt material from deeper down, which can give us a much better idea of what's happening deep down, what the Earth is perhaps made of, sort of deeper down, what processes are happening. They influence the composition of the atmosphere. The fact that we have volcanic activity is the reason we have an atmosphere at all. Volcanoes created our atmosphere early in Earth's history. And even today, they produce gases that influence the composition. Particles can change radiative balance. That's a very fancy way of saying that ash and particles erupted by a volcano can block incoming sunlight. Okay, they can change the amount of energy we see. And after really big eruptions, even in the past 20, 30 years, we see a little dip in global temperatures the following year. Not a huge dip, but a little dip because of the effect of this sort of ash in the atmosphere reflecting back more of the incoming radiation. And they redistribute energy. So remember we talked about hydrothermal vents already. We have energy sort of moving through sort of mid-ocean ridges. And also fundamentally, they create areas of new continental crust. They create land, which is very convenient for us because we like living on land. Okay. So we have lots of different types of volcano, and when you get asked to think of a volcano, you probably think more like the one on the right. Okay, nice steep-sided sort of volcano that you might be a bit concerned living nearby. But actually we have lots of different types of volcanoes. We're just going to talk about 2, and we're going to talk about this one on the left, which is shield volcanoes as well. And it's that really gentle-sided volcano in the back of that picture. That's our shield volcano. Okay, so my slightly trickier question of the day is, which type of magma do you think will be erupted from these two different volcanoes? So you have a choice between your 3 different magma types. So think back to your magma types and their characteristics, and think about which type of magma you think would be erupted from each of these, or give them their shape. Okay, a few last seconds for people to put what they think. Okay. Ooh, well done, guys. Okay, so B was the correct answer, and the majority of people got that. Okay, so tell me, someone, why did you put B? Why did you think that those particular shapes were associated with those types of magma? Yes?
So since basalt is more runny, like I feel like it won't stack up more.
You've
Since the other ones are, like they like get higher and higher.
Absolutely, you've got it. It's as simple as that, which is that basaltic magma, remember, is more runny. It flows really nicely. And so if you're going to erupt basaltic lavas at the top, they'll flow really nicely outwards, and they'll flow sort of relatively fast, and so you end up with this nice gentle slope. Whereas you're right that andesitic magmas and lavas and rhyolitic magmas and lavas, they're sticky, they have high viscosity, and so they tend to stack together, and they don't flow outwards to create a nice gentle slope. They instead form a much steeper slope. So which of these two would you prefer to live next to? The shield is probably going to be easier. The stratovolcano might be alright for a while, but you never know what's going to happen. Okay, because associated with that shape is also the type of eruption. Remember, we said that basaltic magmas have a relatively low gas content because that gas can escape really nice and easily, and they're runny, so you don't get nice explosive eruptions. Whereas when we have stratovolcanoes, we have more andesitic and rhyolitic magmas, and they have a higher gas content, and they don't flow so easily, and so you end up building up this pressure, and so they have much more explosive eruptions. Okay? Does anyone know which volcano this is in the right, by the way? Mount Fuji? Yeah? It isn't actually Mount St. Helens. Mount St. Helens doesn't look that pretty anymore, unfortunately. This is actually Mount Fuji from Japan, and this is from Hawaii on the left. Okay. So, you have to think a little bit now. I want you to give me examples of tectonic boundaries where we get volcanic activity. So what sort of boundaries do we get volcanic activity at? Thinking back to last Wednesday. Yes? Subduction zones, absolutely. Subduction zones are really good ones because we have that ocean lithosphere sinking back into the mantle, and as it does that, water gets squeezed out and we get melting of the mantle above that. Absolutely. So apart from subduction zones where we have both continent and ocean, what type of other boundaries do we have volcanic activity at? We do get them at hotspots, absolutely. So not necessarily a boundary, but hotspots are where we get lots of volcanic activity. Where else would you go to find volcanoes today? I think I heard muttering mid-ocean ridges, divergent boundaries, okay? We're creating new crust. So that volcanic activity there is creating this area of new crust. So I think you've got all of the ones I got. So we have our island arcs, so where we have subduction of ocean and ocean coming together. We have continental arcs, or the sort of line of volcanoes in a continent, because we have subduction of ocean crust where they meet. We have rifts. Remember, we have continental rifts, where we have our African Rift Valley today. We have that crust being pulled apart. We have mid-ocean ridges, where instead of having continental crust being pulled apart, we have ocean crust being pulled apart. And then we have our hotspot. Okay, so now have a look at my little diagrams and think, how much continental crust do you think is going to get incorporated in each of these different settings? So have a quick think, talk to your neighbor for 30 seconds or so, and think in turn about what type of magma you might find at those different places. Okay, so let's start with an easy one. Let's start with the right-hand side here. How much continental crust do you think goes into magma that ends up being erupted at the mid-ocean ridge? Nothing, right? More or less none. There's no continent there to contribute. So what type of magma do you think is erupted at this sort of setting? Basaltic, absolutely. So there's really very little continental crust there, so we've got basaltic magma. How about our hotspot? How much continental crust are we getting into our magma at a hotspot? More or less none. Very little again. So what type of magma do you think gets erupted here? Basaltic. And you know that's true because remember, we have our Hawaii hotspot, and we know that we get those really dark, basaltic, easy, sort of nice shield volcanoes there. Okay, what about our rift? How much continental crust do you think gets incorporated here? Quite a lot. Yeah, any mantle that comes up through that has to melt all its way through that continental crust. Okay, so this type of boundary, what type of magma do you think we get if we have a lot of continental crust? Rhyolitic, okay? So let's move on to our continental arcs and our island arcs, and these are both the same fundamental processes going on. How much continental crust do you think we get incorporated in? Everyone's going, medium. Medium, yeah, absolutely. So what type of magma do we most likely get? Andesitic. And is there a clue in the name that matches with any of these? What was our lovely example of a real-world setting today where we have continental arcs, we have subduction and the Andes? We've got andesitic magma being erupted at the Andes. Makes sense, right? Okay, so that's basically a little summary of what we did. Now thinking about that, what type of volcanoes, what type of dangers are associated with these different environments? So remember we said that shield volcanoes form from basaltic lavas, and so these don't tend to be explosive. They tend to be gentler eruptions, whereas our andesitic and our rhyolitic magmas tend to build up that pressure and go bang. Okay? So we get more violent eruptions at things like subduction zones, at rift valleys. And I should say that this is a massive oversimplification. Okay, you can go in different settings and find lots of different examples, because it's a very complicated process that's going on. Each volcano is a little bit different, but there's at least a rough idea there of how this all fits together. And so, hopefully, by yourselves, you can think about the different types of boundaries here. So we talked about the Aleutian Islands, where we have that subduction zone, we have the Andes, we have the Cascades, where we have those big explosive eruptions. I keep saying reactions of eruptions, okay? And you can think about the mid-ocean ridges, where we have that nice sort of basaltic flow. And my hotspot example there was specific for Hawaii. So if you get hotspots under the continental crust, then it might get a bit more complicated. Okay, so there you can see a little summary map of where the different types of boundaries and different types of volcanic activity occur for your notes. Okay, because volcanic hazards, this is the bit that people like. So we have our basaltic volcanoes that are rarely hazardous. You might get lava flows going where you don't want them to go, but you're probably going to know it's happening. But stratovolcanoes present much, much more hazards to us as people. And these are some of the, not an exclusive list, but these are some of the things that you should be scared of. So first of all, lateral blasts, pyroclastic flows. The second is tephra and volcanic ash. lahars, which is a funny word for meaning mud flows, poisonous gases, tsunamis, and then of course we have the longer term impacts on society. So things like destruction of agricultural land can lead to famine. Not so much today, but definitely in the past we saw this. So this is Mount St. Helens before and after, and you are much, much too young, and even I'm too young to remember Mount St. Helens, but it was the last time we had a really huge eruption in the US. And you can see that basically the whole top of that mountain got blasted off. And I've got a little YouTube video there. You can find more information in your textbook as well. But this, instead of going up, which a lot of volcanoes will do, this was the first time that really a volcano, basically the sides, so there was a big earthquake, and the side slid away, and that released the pressure, and everything came out sideways. And that's why it actually killed a lot of people, because we weren't expecting it to come out sideways, we were expecting it to go up. And so if you ever see those photos of all the trees laid flat, this is our lateral blast. And associated with those, we have what we call pyroclastic flows, which are truly terrifying. These are flowing clouds, they just look like ash clouds flowing down the mountainside, of hot rocks and gas. They're very hot, several hundred degrees Celsius. You take a breath, it basically cooks you from the inside out. They go very fast, 400 miles an hour. Good luck at running one of those. They travel very far, so greater than 60 miles in some cases. And they will also go uphill. So unlike some things like floods you can escape by going to higher ground, this doesn't necessarily save you. So if you are anywhere near a pyroclastic flow, you're basically screwed. Okay? And this is sort of a lot of the damage is done in this way. And Mount Pelée in 1902, 29,000 people were killed instantly. Their main city was just underneath the volcano, and you can go there today, and you can basically see they had this grand old opera house that just got sliced off at the stairs. You can go up the stairs and there's basically nothing up there. So these are very dangerous. Tephra and volcanic ash. We saw an example just 3 years ago now from Eyjafjallajökull of how ash does not necessarily mix very well with airliners. And this is something that we haven't had to deal with necessarily in the US in recent history, but sooner or later we will. So these ash streams can travel really high, travel hundreds of kilometers, and that ash is heavy. It's really heavy. It's basically ground up bits of rock. And so if you pile up enough of it, it can do a lot of damage to structures as well. Okay, and very large eruptions can obviously block out the sunlight. And then when we talk about really huge eruptions, we talk about nuclear winter type effects. So where we can really do a lot of damage to the biosphere. Okay, lahars. So I have a little very quick video to show you of a lahar from Japan. And these are hot mud flows. So where we have this ash collecting, whenever there's the next rainstorm, you can see these enormous mud flows come down. And when these things sort of settle out, when they stop moving, they set more or less like concrete. So these things are not good to get in the way of. And often they're really quite hot as well. And this can be at the time. If it's raining when these eruptions occur. But it can also happen up to years afterwards. And this is something that we've mapped out quite carefully in the US in different places where our lahars could flow. And there are building codes now to adjust to that. And then lastly, we have three that don't have sort of pretty pictures associated with them, but they can also be very dangerous. So these volcanic eruptions release a lot of carbon dioxide, nasty sulfur dioxide, hydrochloric acid. It can turn lakes a little bit acidic. Big clouds can roll down and smother towns. Tsunamis, if you get a big enough eruption and you get landslides and rock moving, then that can send out a tsunami in the same way that changing the sea floor during an earthquake can. And then, of course, we have our long-term impacts as well. Okay, so my question for you is, what should you be most scared of if you're near a stratovolcano during an eruption? What should you be telling your friends that you need to escape from? Okay, one more minute, guys. Okay, let's take a look, see what people thought. Good, yes, pyroclastic flows. Don't go near them. Okay, so we did the first part of the rock cycle today. So we talked about magma that cools and crystallizes to form igneous rocks, but there's a whole bunch extra to the rock cycle, and that's what we're going to do on Wednesday. So Wednesday, geologic time and sedimentary rocks.